Welcome to ReneEnergy.com on YouTube, the hub for all things renewable energy and sustainability. Our channel is dedicated to bringing you the latest innovations and insights in green energy, including cutting-edge developments like green hydrogen. Whether you're a sustainability veteran or just beginning your journey, we have something for everyone. Join us on this channel to explore inspiring projects for a sustainable tomorrow. We bring you the latest in renewable energy, sustainability, and cutting-edge technologies. And don't forget, for more in-depth information and resources, visit our website and subscribe to our newsletter for the latest updates and exclusive content. Hello and welcome back to ReneEnergy.com. In the previous video, we took an in-depth look at the fundamentals of green hydrogen combustion in cement kilns, covering topics such as the principles of hydrogen combustion, comparisons with traditional fuels, burner design considerations, and flame characteristics. Building upon that knowledge, in this video, we'll explore the energy efficiency and emission reduction strategies that can be employed in hydrogen cement plants to maximize the environmental and economic benefits of this innovative technology. Assessing energy efficiency. Before we dive into the strategies, let's first define what we mean by energy efficiency in the context of cement production. Energy efficiency refers to the optimum utilization of energy resources to achieve the desired output while minimizing waste and losses. In other words, it's about getting the most out of every unit of energy consumed in the production process. To measure and track energy efficiency, cement plants rely on key performance indicators, or KPIs. These KPIs provide a quantitative measure of how effectively energy is being used and help identify areas for improvement. Some of the most commonly used KPIs in the cement industry include specific energy consumption per ton of clinker or cement produced, thermal energy efficiency of the kiln system, and electrical energy efficiency of grinding and auxiliary processes. When benchmarking the energy efficiency of hydrogen-fired kilns against conventional fuel systems, it's essential to consider a range of factors that can influence the overall efficiency. These factors include the properties of the fuel itself, such as its calorific value and combustion characteristics, as well as the design and configuration of the kiln system, the heat transfer mechanisms at play, and the operational practices employed. By carefully analyzing these factors and identifying areas where efficiency can be improved, cement plants can optimize their hydrogen-fired kilns to achieve higher energy productivity, reduce operating costs, and minimize their environmental footprint. Optimization strategies. Now, let's explore some of the key strategies that can be employed to optimize energy consumption and minimize emissions in hydrogen cement plants. One of the most effective approaches is process optimization, which involves a systematic analysis and improvement of the various subprocesses within the cement production chain. This can include optimizing the kiln system itself, such as the preheater, calciner, and cooler sections, to ensure that heat is being efficiently transferred and utilized. It can also involve implementing better raw material and fuel quality control measures to minimize variability and ensure consistent performance. Another important aspect of process optimization is the recovery and utilization of waste heat. Clinker coolers, for example, generate significant amounts of high-temperature air that can be harnessed and used for various purposes, such as preheating the raw materials or generating steam for power production. In addition to process optimization, the adoption of advanced process control and automation systems can greatly enhance the energy efficiency and emission reduction capabilities of hydrogen cement plants. Technologies like Model Predictive Control, or MPC, can be used to optimize the kiln operation in real time, taking into account a wide range of variables and constraints. Real-time monitoring and optimization of combustion processes is another key application of advanced control systems. By continuously measuring and adjusting parameters such as fuel flow, air-to-fuel ratio, and flame temperature, these systems can ensure that the hydrogen combustion process is always operating at its optimal point, minimizing fuel consumption and emissions. Upgrading to energy-efficient equipment and technologies is another important strategy for improving the overall efficiency of hydrogen cement plants. This can include installing high-efficiency motors and drives, variable frequency drives, VFDs, for fans and pumps, and energy-efficient grinding systems, such as vertical roller mills or high-pressure grinding rolls. These technologies not only reduce the electrical energy consumption of the plant but also improve the reliability and longevity of the equipment, reducing maintenance costs and downtime. Waste heat recovery. Waste heat recovery, or WHR, is a critical component of any comprehensive energy efficiency strategy for hydrogen cement plants. Cement production is an inherently energy-intensive process, and a significant portion of the energy input is ultimately lost as waste heat. The primary sources of waste heat in a cement plant include the exhaust gases from the preheater and clinker cooler, the radiation from the kiln shell, and the hot air from the clinker cooling process. By capturing and utilizing this waste heat, plants can significantly improve their overall energy efficiency and reduce their reliance on external fuel sources. There are various WHR technologies available, each with its own advantages and applicability. One common approach is to use the waste heat to generate steam, which can then be used for power production through a cogeneration system. This allows the plant to generate its own electricity, reducing the need for grid-supplied power and lowering operating costs. Other WHR technologies include organic Rankine cycle, ORC, systems, which use an organic fluid with a lower boiling point than water to generate power from low-grade waste heat, and Kalina cycle systems, which use a mixture of ammonia and water as the working fluid to achieve higher efficiencies. In addition to power generation, waste heat can also be utilized for other purposes within the hydrogen cement plant. For example, it can be used for steam reforming or thermochemical water splitting, which are processes that produce hydrogen from water using heat as the primary energy input. This integration of WHR with hydrogen production can further enhance the sustainability and self-sufficiency of the plant. Preheating the combustion air or the hydrogen fuel itself with waste heat is another effective way to improve the overall efficiency of the combustion process. By raising the temperature of these inputs, less fuel is required to achieve the desired flame temperature, resulting in reduced fuel consumption and emissions. The economic and environmental benefits of implementing WHR in hydrogen cement plants are substantial. By reducing the need for external fuel sources and generating their own power, plants can significantly lower their operating costs and improve their profitability. At the same time, by reducing their energy consumption and associated emissions, they can contribute to the global efforts to combat climate change and promote sustainable development. Hybrid fuel systems and transitional approaches. For cement plants that are considering a transition from conventional fossil fuels to green hydrogen, the prospect of a complete switchover can be daunting. Fortunately, there are hybrid fuel systems and transitional approaches that can help make the process more manageable and less disruptive. One such approach is co-firing, which involves burning a mixture of hydrogen and conventional fuels, such as coal, petcoke, or natural gas, in the kiln. By gradually increasing the proportion of hydrogen in the fuel mix over time, plants can progressively reduce their reliance on fossil fuels while minimizing the impact on kiln operation and product quality. The co-firing process does require some modifications to the burner design to ensure efficient mixing and combustion of the blended fuels. The fuel blending ratios and their impact on combustion characteristics must also be carefully considered and optimized. Another transitional approach is to implement a staged transition, where the plant gradually increases the percentage of hydrogen fuel over time, allowing for a more controlled and predictable adaptation of the kiln operation and control strategies. This approach allows plant personnel to gain experience and confidence in handling hydrogen, while also providing an opportunity to fine-tune the process and address any challenges that arise along the way. Case studies of successful hybrid fuel system implementations in cement plants provide valuable insights and lessons learned for others considering this approach. These studies demonstrate that with careful planning, engineering, and operational adjustments, cement plants can successfully integrate hydrogen into their fuel mix and achieve significant reductions in emissions and fuel costs. Conclusion. In conclusion, energy efficiency and emission reduction strategies are essential for maximizing the benefits of green hydrogen in cement production. By assessing energy efficiency using KPIs, implementing optimization techniques, leveraging waste heat recovery, and adopting hybrid fuel systems or staged transitions, cement plants can significantly enhance their environmental and economic performance. Take the first step towards a sustainable future for your cement plant. Download our comprehensive technical feasibility guide on green hydrogen integration now at link in the description below and start your journey towards energy efficiency and emission reduction. Thank you for watching this ReneEnergy.com video on energy efficiency and emission reduction strategies in hydrogen cement plants. Stay tuned for the next video, where we'll delve into the technical feasibility assessment and cost analysis of green hydrogen integration in cement production. Don't forget to like, share, and subscribe to our channel for more valuable content on sustainable energy solutions. See you in the next video. Thanks for tuning into the ReneEnergy.com YouTube channel. We trust you found this episode enlightening and motivating. There's a world of innovation and opportunity in sustainable energy, and we're delighted to share this journey with you. Stay in the loop with the latest on renewable energy and sustainability by visiting our website and subscribing to our newsletter. Your support is immensely appreciated, it's truly invaluable to us. Don't miss our next video on new trends in renewable energy. Follow us on social media for the latest updates. Enjoyed the video? Like, subscribe, and share for more green insights. Thanks for watching.